Okay, so today we're going to be doing related rates, but specifically focusing on the cone problem. Okay, the cone problem is a little bit different than other related rates problems because we have two variables in there that are changing over time. Because as one changes, the other changes as well, and we'll talk about it in a second. So we have a conical water tank that has a radius of 3 meters and a height of 6 meters. Water is flowing into the tank at a rate of 2 cubic meters per minute. How fast is the water level rising when the water is at 2 meters high? So the first thing we're going to do is we're going to draw a picture of our cone, okay, our conical tank. So we draw a cone. Okay, cones are really easy to draw. You start with an ellipse, a couple lines, you show your height and your radius. So let's draw our situation here. Well, we know the height of my tank. Height is 6 meters. We know this radius is 3 meters. Okay, that's the information they gave us. They also said that we have water that's flowing into the tank. So the water is coming in at a rate of 12 cubic meters per minute. Okay, so how fast is the water level rising when it's at 2 meters high? So right here is 2 meters. Okay, so what is the height changing when it's that high? Okay, so let's figure out what we got. Well, obviously this 12 cubic meters per minute, that is our change in volume over time. So dV over dt is positive 12 cubic meters per minute. Okay, what gives it away is the cubic meters. That's giving me volume per unit of time. So that is my dV over dt. Now, they want to know how fast the water level is rising when it's 2 meters high. So they're asking us to find dH over dt, specifically when the height is 2 meters. That's what we're looking for. Okay? Now, we're using volume of a cone. So the equation for the volume of a cone, V equals 1/3 pi r squared h. Okay? Now, if we were to take the derivative of this with respect to t, the way it is right now, okay, that would give us dv over dt equals pi over 3, and then it would be 2r h dr over dt plus r squared dh over dt. Okay? Now, there's one problem with that. If we do that, we end up with variables and terms that we don't know. For instance, we don't know what r is. So how would I deal with this? How would I plug those in? And I don't know what dr over dt is. Okay, so, and I'm looking for dH over dt, which means that there would be 3 variables that would be unknown to me. And that causes a problem. Okay? So basically, we cannot do it this way. So we have to think of it in a little bit different way. Okay? So we can't do this. So what I'm going to do is I'm basically going to go back to something that we learned in geometry. Okay, we're going to get rid of my r because dr over dt is what's keeping me from being able to do this problem. So I'm going to substitute r by going back to what I was given over here and showing that, look, this triangle here that's created by my height and my radius is similar to this triangle here that I'm using. So I'm going to use the idea of similar triangles to figure out a proportion of my height and my radius. So my radius and my height are always at this proportion of 3 over 6. Okay, so I'm going to solve this for r, and I get 1/3 h. So r is always 1/3 of h. Now, that would allow me to find out what r is, but that also doesn't allow me to find out what dr over dt is, that rate of change, because it's different. So what I have to do is I'm actually going to use this and plug it into my equation to get myself down to just one variable on the right. So I'm going to rewrite this in just terms of h. So this is 1/3 h squared times h. So all I did was just plug in r being 1/3 h into my volume equation, because that proportion should always hold true. And now I don't have r when I differentiate, I only have it in terms of h, which makes my life a ton easier. So we'll simplify this before we get started. And 1/3 squared is 1/9, so this is pi over 27 h cubed. So now, when I do this step and I take the derivative of this with respect to t, I only have two variables to worry about. So I get dv over dt equals, bring the 3 out front, so that gives me pi over 9 h squared dh over dt. Do I know what dv over dt is? Yep. Do I know what h is? Yep. So I can solve for my dh over dt. So now we just plug in. So we get 12 equals pi over 9 times 4 times dh over dt. Now I'm going to multiply both sides by 9 over 4 pi times 9 over 4 pi, because this 4 and that 4 will divide out. Pi divides out pi, 9 divides out with 9, leaves me with my dh over dt. And then here 4, so that's 3, that's 1, so 9 times 3, that's 27 over pi, and this is meters per minute. And that's my answer, which is approximately 9, because pi is 3.14. So the only extra step that we have to do when we're dealing with cones is this proportionality. Setting up a proportion here and plugging it into my equation to get it in terms of one variable. Okay, which is something we learn how to do also, or what we have to do in optimization that we'll do later, where we take one equation that's our limiting factor or our ratio and plug it into our original one. Okay, so this is our first taste of kind of like optimization. But that's the only difference with our other related rates problems, is that we have, for a cone, we have to deal with the fact that we're dealing with more than one variable.